R modules. Then that's right. But let's be careful about this. So we do our usual diagram here. This is, of course, the map that takes the order pair AB into a tensor B. Yes, that should go. And it's easy to verify this is not the map, right? Nobody here. Right? And so this induces this map bar. Basically what it does is just reverses all the coordinates in the tensor, right? So in particular, in general, G bar of a sum it's probably pretty clear this map is onto. Am I correct? Right, it's this is onto. Because of course anything here can be written in that form, and it's obvious what it comes from. But once again, I think it's not completely lucid that it's one-to-one, right? Because again, you might ask yourself, okay, what does it mean to be in the kernel of this, right? Not completely sure how to write that down, even though it looks obvious. Now, one thing that you could do is you could go back to the roots of this and say, well, okay, what does this mean? This is just, free, this is free group on ordered pairs A, B. This is a free group on ordered pairs B, A. Do some kind of homomorphism, switching out the variables, and say, okay, look, the kernel is essentially the same thing. It's just an automorphic image in this, blah, blah, blah. But there's another way to do this that might be kind of cooler. Anybody see what else we can do?
We try and just go the other way.
Right, that's a good idea. So what we have so far is this. And what this does is it takes some AI tensor PI into the sum of PI tensor AI. But of course, there was nothing special about me doing this one first. Bar, called stage bar. What's good for the goose is good for the gander. There should be another map in this direction. And this composition should be identical. And you can do it the other way. And so now I've taken 4.5 minutes for our valuable time to prove the obvious, right? But at least we have this down, and this kind of illustrates showing that this map right here is one-to-one is not as completely lucid as showing that that thing is onto, right? But this little augmentation of the diagram makes it much easier. Right? So that's kind of a good technique to know. So let's go back to the last theorem that I at least hinted at last time, and that was the right exactness of the tensor product. So theorem. If P is an R module, then more precisely, um, if the short exact sequence of our modules is exact sequence so in a certain sense, the tensor product is dual to the Hom, right? It's always right exact. It tends to preserve the ontoness, right? And I don't have to worry about a contrarian case here because the order is preserved for the tensor product. And notice my previous theorem says that it doesn't matter if my fixed D is in the first or second pair, right? And that was kind of another point of what I did there. Okay, I will prove one direction of this. I'll prove this forward direction here, and I'll let you think about the other one. This one I think is, well, actually, I think 2 out of 3 things that you're not to have. Okay, so I'm going to show that this is onto, right? Well, let C tensor D be any single tensor by the fact that G is onto, since G is onto, there exists a B in B such that C is G of B. Therefore, if you look at C tensor D, a random single tensor, this is G of B tensor D, which is G tensor 1D acting on the tensor B tensor. So in particular, every C tensor D is an image of D. And of course, C tensor D is generated by the single tensors. Therefore, the image of G tensor 1D is all C tensor. So G tensor 1. Okay. Next, I want that the image of that tensor 1D made the kernel of G tensor 1D. And this one's also not too bad. So notice that F So if I look at, so if I do F tensor one, then G tensor one, this is and FG is the zero line. So when I do this composition here, this composition map zero. Therefore, the image of F tensor one D must be contained in the kernel of G tensor one D. That's the composition of maps. And finally, as always seems to be the case, we have the toughest one is going to be the kernel is between the image. So finally, going from the kernel between the image. So this one here, I'm going to kind of break things apart a little bit. So let's consider first. And here pi just does what I think it does. So pi of B tensor D is B tensor D plus the coset image. Now, I just told you what pi does on a single tensor, but if I tell you what it does on a single tensor, I've told you what it does everywhere generators. So in general, you can replace this with sum of tensors, right? Now, I also get this other homomorphism. I'm going to move this along from here. Also, there exists this guy. I'm going to show you how this one is induced here. What this does, so actually, I'm going to show you what the composition does. When I do okay, so what does this do to a single tensor? This is so really what happens here is so my input for this here is going to be my output is going to be the sum of GPI tensor. Now, what's the first thing that I've got to worry about? Well defined. Can somebody explain why this thing is going to be well defined? Well, so suppose that you have two ways to represent this coset, some BIDI and some BI prime DI prime, right? What can you say about the difference between those coset representatives? They belong, they're in the image of F tensor one, right? Which is contained in what? Which is contained in the kernel of this. Therefore, you get the same output here, right? Well, fun as image of tensor one and kernel. So, good thing we did that one first, huh?
To show that size isomorphism.
Yeah, but I don't even need that much, because what we have now is that's exactly what we're going for. So what we have is we have well, so what I want to do is actually what we want to do is we want to show it actually suffices. Suffices to show this is what we want. Because remember, my ultimate goal is to show that this is equal to the kernel of G tensor one. Now, the kernel of G tensor one is a submodule of this, right? Now, everything in the image is killed in this map, right? Because this is a zero thing. So if you have equality between the kernel and the image, that'll make this 1-to-1. And if this is 1-to-1, that means that because of the way this is defined, that means the kernel actually has equal. Everybody cool with that? So really, this is all we got to do to show that this thing is really 1-to-1. So I'm going to set up a map in the other direction, as you might expect. This is your product. Now I'm going to start off this way. Consider eta C cross D back into and I love these things because they only have to be bilinear, right? But this one we are going to have to check a little bit. I'm going eta the order pair CD to equal remember pies, so I'm being sloppy. Pi is this projection here. Yes.
Should that be C tensor E?
No, it actually, because it's too hard for me to map things tensor, I'm going to actually use this thing. I'm going to lift this to a map, right? This is actually, I'm going to use this eta to build something from the tensor product, right? It's too hard for my pea-sized little brain to start with the tensor product, so I start with that cross product and build it from there. So this is what I want to do. Of course, this element is indeed over here, right? I projects onto this. And how do I determine B? B is such that G and B equals C. And There's a little alarm siren going off. Rendition, right? Because again, what we need to worry about this being well defined, right? And so, note. Suppose B1 is such that B1 C as well. So I'll pick a different, perhaps pre-image. And notice that G of B minus B1 like, is equal to 0. Therefore, there exists A such that F of A is B minus B1. Right, using the exactness of the original A to B, C thing. And so what this means is, right, F of A tensor D is in image of F tensor 1D, which is contained in the kernel of G tensor 1. So when you do G to that, you get 0. So in other words, pi and so in particular, sign right here. F of A plus B1 tensor B, which is so we have that this is well defined. Okay. What do we have? We have eta is well defined. And it's bilinear. It's pretty easy to check that this is a bilinear map. And that's the whole point of doing these bilinear maps. So there is a unique eta R. Into and see, this is my point, right? Now I've looked at this bilinear map to this thing, which is it's too hard to make construct in general, or it's too difficult for me to want to fool with that way. Such that when you look at eta bar C tensor D, this is and so for any generator, so if you have any C tensor D, then if you look at this is which is C tensor. So in particular, this takes every generator, the generator itself, so. uh, So. uh, In a similar fashion. That when you do it in the other order, that is. AR. The identity on. So in particular. That's. Okay, and so that gives, and of course you can see that, we dashed off 2 out of 3 of these pretty quickly, and this one required a bit of construction. Okay. Any questions? Okay, let me give you an example.
That's. Moving the other direction, we just take the, which one? R?
Yeah, take D equals, again, with the other direction, so think about how to do it, because I said I only did one direction on this, if you take D equals R, I think that may work for everything. Because in fact, well, I'm gonna record this there, and we actually did this last time, let me give you a quick example. If 0, A, B, C, 0 is a short exact sequence, then A is exact. So what this theorem tells me is, well, the theorem actually said this, so I don't even need 1-to-1 on F to make this work, but even if F is 1-to-1, it perhaps is going to fail. Do we have an example of this? Well, I think that would be important. So tensor product behave very well with respect to onto, and this is part of the exactness. Tensor product can be a little flaky with respect to 1-to-1, and we'll see some of the strange behavior here. So here's an example, a numerical example. Or I'm going to treat these two Z2s the same notation. Now, let's see if we can figure out how this short exact sequences work. And in fact, I'll write everything out in gory detail. Okay. Oh, Jim's doing the easy part, right? I mean, that has to work. What about where does one go? It has to go, any element, so this is an element of word two, this has to, one either has to go to 0 or to 2, because it has to go to an element of word two. One, this is going to be very boring, it goes here, so. And this is basically just going to be mod 2, right? So in this other step here, what happens is, seriously, what a total teaser. So in this other step right here. So that's the way I was going to work this word. And it's clear, isn't it, that it's exact here in the middle, right? Because the image of this is precisely this. This is clearly on students, right? So this is an exact sequence. I'm going to call this F. F is 1 to 1, but tensor products do not always behave nicely with respect to 1 to 1 maps, in particular this one. So by the way, you also have to figure out what the tensor is with to kind of make this work out the way you want to. What did anybody have an idea what we want our D to be here? Yeah, I think it's trust. So we have F. Now let's look at F tensor 1. Now, notice in each of these, well, remember, this is isomorphic to Z2. I'm glad I did that example. Y'all remember that example? So this only has 2 non-zero elements. It has 0 tensor. And in fact, everything in here was a single tensor, right? That's another 0 tensor 0 goes to 0 tensor 0. Right? And the only non-zero tensor here was, there were actually 4 tensors here, but 3 out of 4 of them were 0 tensors. Right? This goes to 2 star tensor. Right. And you might see the problem now, because this is 2 times 1 star. And now swings across the tensor. So tensoring with Z2 here turns a map that was 1 to 1 into a 0 map. Right? I mean, it doesn't really get any worse than that. Right? It turns into 1 to 1 and something that takes everything to 0. Right? So you can see that it is sort of hopeless to get this theorem back in general, because even if you have a short exact sequence like this one, you're only guaranteed exactness. You might lose one to ones in first math, no matter, in general. So any questions? All right, so. Okay. Here's the good news. And this theorem is very much like the Hom. This was pretty easy to implement, so I'm gonna leave this proof as an exercise. But theorem. Yeah. 0, A, B, C, 0. Is split. X. And so is. So just like the Hom, it's split exact. As well. Yes.
So I have a question. C4 tensor C2 is also C2?
Yes, it is. Yeah, it is. In fact, there's a theorem that says if you have Z mod M, tensor over Z with Z mod N, then tensor product of those two is Z mod D, where D is the greatest common divisor. Right, so, so split exactness like before behaves well. Let me give you a couple of nice theorems. The first one I proved before, the second one is going to appear on your homework. The first one, just for the sake of recording in your notes, we've done this via example, because I got so excited I went ahead and did it. Theorem 688. If A is an R module, then then this one before. And the next one's really kind of cool. Adjoint associativity. There's a more general version of this, but again, I'm just the commutative R modules. It's called adjoint associativity. Let A, B, C be R modules. There is an R module isomorphism. Home R this is actually isomorphic to home R A home R. this one's, this one I'm gonna ask you to kind of do in your homework. But this one's kind of funny to sort of wrap your head around, right? Because what you need is a homomorphism from the homomorphism tensor product of C to the homomorphisms from A to the homomorphisms B to C, right? So it's an interesting exercise. Just think, how would you do this, right? So you have whatever we call this, big important looking thing. And your input is some homomorphism from here to here, right? So this of this, when you plug this in, C, you start with this F, with the homomorphism from A tensor B to C. Now you need to have it output a homomorphism from A to the homomorphism to B, C, right? So what is phi of F? It should be a homomorphism from A into the homomorphism from B to C, right? So when I'm plugging an A to this has to be a homomorphism from B to C, right? So this itself has to be a homomorphism from B to C. So what should this be? How about something like F of A tensor B? Something like that, maybe?
That makes sense.
Right, but the worst part, I think, of the homework, it's not too bad to show when I give you the homework problems, just kind of thinking, wrapping your head around it, because there's a lot of arms here, right? But in fact, the proof, once you wrap your head around it, it's not too bad. I will give you some advice for the fact. The best way to do this, I think, is not to construct this phi and then show it's one-to-one and onto. Construct the phi and then construct its inverse. Say, figure out how to get back here and show that when you compose them. I think that's actually the easiest way to do it. Okay. So let me leave you with a couple of gems before we get into flatness, which is flatness section is very, very short. Theorem 6, 8, 10. Tensor product commutes with directs. So if you ever hear somebody drop those kind of puzzles, oh, the tensor product commutes with direct sum, here's what it means. But A and AI, B and BJ, be R modules. I've got this big collection of R modules. Number one, the direct sum by and I of AI. It's B. It's isomorphic. Direct sum AI tensor. So in other words, it's just behaves like you would expect multi-bit distributes, right? That's kind of what it is. And two, if you have A tensor with the direct sum J and J, this is isomorphic. The direct sum J and J of A tensor. So tensor product plays nicely with the direct sum. And here's a sketch of the proof. let me just show you how to do it. How would you show such an isomorphism? You would do what I've become so fond of doing by setting up bilinear maps and saying, oh, look at me. What we're gonna do is consider the bilinear map. Okay, so I want to go from, the correct symbol, AI. Cross B. To, the, correct sum across. Given by. So here's my ordered pair. So and there's the direct sum of a bunch of tensors, right? Notice it's important here that almost all of these AIs are zero. That's direct sum part is important. This is the bilinear map. So that's my sketch. And from this,
Is it important because otherwise we might put in some tensors?
well, right, it's gonna show, because what you're gonna need is finite sums, right? Of course. Let F be a free R module, then if you have F, notice by the way that this is a big generalization of theorem, I guess it was 688, because in 688 we have a free module with only rank 1 here. Then F tensor B is isomorphic to the direct sum of some number of copies of B. And how many is this? Where cardinal I is equal to, or I'm sorry, because here I'll sketch this one. F that's what that means. Now replace this F with this and apply that theorem. Right, so F tensor B is isomorphic to the direct sum R B is isomorphic to the direct sum R tensor R B, and by 688 this is isomorphic. And that's enough. Okay, any questions? I will talk about flatness very briefly next time, and then we'll get into modules over PID. Any questions? The math club might be fun today, because I'm gonna do some practical Rubik's Cube, so if you make it, that's great. Otherwise, y'all have a great weekend, and we will see you on Friday.